Hello, this is Mrs. Valdez, and today we are going to look at the section 1.4 Day 1 notes in pre-calculus. And if you would like an essential question when we talk about rational expressions, hopefully by the end of this video we can answer the question, how do you determine the domain of an algebraic expression? And how do you rationalize the denominator or the numerator? So before we get into that, we need to talk about what a rational expression is. And a rational expression is a fractional expression where both the numerator and the denominator are polynomials. And I will show you a few examples of what that would look like. So for example, you could have 2x over x minus 1. You could have x over x squared plus 1. You could have x cubed minus x over x squared minus 5x plus 6. So notice in all of those fractions, both the numerator and the denominator contain polynomials. So when we talk about rational expressions, there's usually some restrictions on the domain, or in other words, on the x's that work in these expressions. So the domain consists of all the values that define, or we might say satisfy, the expression. Restrictions on the domain exist when there is a variable in the denominator or there is an even root in the expression. And we will look at some examples of both of those, whether you have a variable in the denominator or an even root in the expression. So that brings us to our first few examples here. It says to find the domain of the expression, express your answer two ways. So in our first example, we're going to start with something that does not have a variable in the denominator and it doesn't contain a root. So if that's the case, if neither of those things are happening, we say that our domain, the x's that we could use here, are all real numbers. Or when you do this in the interval notation, all real numbers goes from negative infinity to positive infinity. And then remember, you always use round brackets around infinities. So that's another way you could express all real numbers using that interval notation there. Okay, example 2, there's going to be a little bit more work. So notice on the denominator we have an easy factor. And when you're talking about domain, you want to make sure that this denominator here is never going to be 0. So what we're going to do is factor that. So can you think of two numbers that multiply to give you negative 15 and add up to negative 2? And hopefully you're seeing that negative 5 and 3 will do that. So we'll turn this expression into m over m minus 5 times m plus 3. And now notice if I would plug in a 5 right here, I'd get 5 minus 5, which is 0. And then 0 times anything is 0, so I'm going to end up with m over 0. And we can't divide by 0. So that also happens over here if m equals negative 3. So we can't have that be our m either. So here's how you could write this. The easiest way to write it is say m is not equal to 5 or negative 3. You could write this in interval notation by including every number except for 5 and negative 3. So how you would write that is you could go from negative infinity up to, but not including negative 3, And then you're going to join that, so the union with not including negative 3 up to number 5, but not including 5. And then you skip 5, and then you go from the next 5, so you're not including that, all the way up to infinity. So that's how you could write it in interval notation. Probably wouldn't recommend it writing it that way, but you can. All right, so now let's look at some problems with roots in them. And notice both of these examples have even roots, so that causes some issues. You cannot take even roots of negative values. So to solve this domain problem, you take what is in the root, in this case 3x plus 5, has to be 0 or positive. So in other words, it has to be greater than or equal to 0. And then we just solve this. So if we solve this for x, we're going to start by subtracting 5. We get 3x equals negative, or not equals, is greater than or equal to negative 5. And if we divide by 3, we end up with x is greater than or equal to negative 5/3. So that's the easiest way to write my domain. X is greater than or equal to negative 5/3. And that just helps, since we have a square root and it's an even root, that just makes sure that we keep our answer real. I could write this as negative 5/3 to infinity. Now I can include negative 5/3 because x could be greater than or equal to negative 5/3. And then I would go up to infinity, so we put a round bracket around that. Okay, so that's how you take care of a root. Number 4 has a couple of ideas here. So again, we're going to focus our attention on the denominator. The first thing I notice is that 8p minus 16 has a common factor of 8. So I'm just going to rewrite that part as 8p minus 2. All right, that'll just make my solving a little bit easier. So anytime you're asked to solve a problem like this, you take what's inside of that root, in this case 8p minus 2, and normally we would just say it's greater than or equal to 0, but now I just want to say it's greater than 0 because I don't want this to equal 0. Because if this equals 0, well, then I run into a problem where I am dividing by 0, which we know we can't do. So if you want to leave yourself a little note here about this, we're saying just greater than because we can't equal 0 in the denominator. Okay, so that's why we're just saying greater than and not greater than or equal to in this case. So now let's go ahead and solve this for p. I'm going to start by dividing both sides by 8. If you divide 0 by 8, you just get 0. So p is greater than or equal to 2. And if I add that 2 over, I can say p is greater than 2. So that is the easiest way to write my domain. I could also start at 2 and go up to infinity. Now I'm not including 2, so I'm going to put round brackets around both of those. Okay, and notice if I would plug into this expression, if I would plug 2 in, 8 times 2 is 16. 16 minus 16 is 0. Then I end up with division by 0. So that's why we cannot include p equals 2. All right, so there's just a few domain problems for you. We are going to switch gears a little bit and look at simplifying now. So a rule that you should remember is if you had something like x over 2x, it is okay to cancel out these x's and make this 1 over 2. It is not okay if you have something like x squared plus 1 and x squared plus 4. So if you had this numerator and this denominator, you cannot cancel these x squareds, okay? because of the plus 1 and the plus 4 that are attached to them. So you can only cancel in something like this first example here. If you try to cancel like that, I'm going to be very mad at you. That is not okay. You can't do that. Right? Maybe I won't be mad at you, but just don't do it. It's not mathematically okay. Every single problem we look at in this part, your first step is going to be to factor. So that is very, very important. That's why we practiced factoring, because we're going to use it all year long. So we always start with factoring. If we look at number 1, I notice in the numerator I have a difference of squares. 4 and x squared are perfect squares. I also notice that I have an easy trinomial to factor in the denominator. So let's go ahead and start factoring. 4 minus x squared is going to factor into 2 plus x times 2 minus x. All over. In the denominator, think of two numbers that multiply to give you negative 12 and add up to, this is a typo here, this should say plus 4. So add up to positive 4. And then let me think, I think negative 2 and 6 will do that. So I'm going to say x plus 6 and x minus 2. Now you're probably noticing what we want to happen here is we want all of the common factors to cancel. And I don't have any common factors, but I do have these two opposite factors right here and here. So we're going to use what we call the -1 technique. And what that does is if you have opposite factors, you can cancel them, but then you have to include a -1 either in your numerator or in your denominator. And here's why. If I would distribute that -1 into here, I'd have a positive x and a -2, and that's what I have down here. But the -1 just makes sure that I'm not like changing the problem. So this would give us our final answer of -1 times 2 plus x all over x plus 6. And you could, if you wanted to, you could distribute that -1 into the numerator and make it -2x. Oh, -2 minus x. Oops. I don't know why this isn't letting me write. -2 minus x over x plus 6. All right, so either of these answers is fine, but that -1 does have to be there. Okay, so number 2 just has a lot of factoring going on here. I notice in the numerator of this first fraction, I have a GCF. So let's start by pulling out 4x. If I take out 4x, I'm left with x minus 1. And then in this next piece, this is an easy trinomial. And in other words, you can make a diamond. Think of two numbers that multiply to give you -6 and add up to, that's 1x right there. And hopefully you're seeing that that's positive 3 and -2. So in the top up there, we got x plus 3 times x minus 2. Okay, let's work with our first denominator. This is another easy trinomial down here. So two numbers that multiply to give you -3 and add up to 2 would be x positive 3 plus 3 and x minus 1. So that's what the first fraction turns into, and clearly we can't do anything with 4x. So now look at all this stuff I can cancel. I can cancel out my common factors. 4x cancels 4x, x plus 3 cancels x plus 3, x minus 1 cancels x minus 1. And all that I'm left with here is x minus 2. So that's in the numerator. In the denominator, everything canceled, so I could just put that over 1. Or since it's over 1, I could just say x minus 2 as my final answer. Okay. So again, factoring is going to be really important. Our last idea that we are going to talk about, actually we have a division problem. So we're still going to do some factoring here, but for this one, I'm going to start by rewriting the problem. So you may have heard keep, switch, flip, or keep, change, flip, depending on who you've had for algebra in the past. So we're going to start by keeping this first fraction as 5x over 3x minus 12. I'm going to switch to multiplication, and then I'm going to flip and put the x squared minus 6x plus 8 in the numerator, and then the x squared minus 2x goes in the denominator. Now let's factor like we did the previous problems. Up here, this is an easy trinomial, so we can find two numbers that multiply to 8 and add up to -6. So let's do that. So this is going to equal 5x. And then over here, hopefully you thought of two numbers that do that. It's going to be -4 and 2, so x minus 4 and x plus 2. All right, we have a GCF in this part, and then this was an easy factor. Take out a 3 there, and you're left with x minus 4. And then we've got another GCF here. You can take an x out of x squared and 2x, leaving you with x times x minus 2. All right, so now we're looking for our common factors. Oh, I have a mistake written here. This should be a -2. It's the only way you're going to multiply to +8 and add to -6 is if that is negative. So that cancels down there. The x minus 4s cancel. And also this single x cancels out this single x. So I am just left with 5/3 as my answer. So all of that just reduced down to 5/3. Okay. Last thing we're going to talk about is rationalizing the denominator or the numerator. There's some cases where that is helpful, which we're probably going to look more at in semester 2, but that's okay. So when you are asked to rationalize the denominator, it means you cannot have roots in the denominator. So in a problem like this, you're going to multiply by the conjugate of the denominator. So in this problem here, we've got 2 over 3 minus root 5. The conjugate is 3 plus root 5. So I need to multiply the top and bottom of this fraction by 3 plus root 5. Remember, you always have to multiply the top and bottom by the same thing. This is just a fancy way of writing 1, and you can multiply anything by 1. It's not going to change it. So let's go ahead and FOIL this out. So I'm going to show you this the long way, and then I'm going to tell you a trick. So in the top, we just have to distribute. This ends up being 2 times 3 is 6. 2 times root 5 is just plus 2 root 5. In the denominator, when we FOIL this out, my first times my first is 9. My outsides is plus 3 root 5. My insides, I have minus 5 times 3. Well, that's minus 3 root 5. So I have that. Notice those are going to cancel. And then root 5 times negative root 5 ends up being minus root 25, which is just minus 5. These two terms, when you rationalize the denominator, are always going to cancel out. So this is gone, and now notice in the top, we just have 6 plus 2 root 5, and we can combine 9 minus 5 is 4. Since all of these coefficients, the 6, the 2, and the 4 are all divisible by 2, you can take those and rewrite that in simplified form, 3 plus a single root 5 over 2. So now there's no roots in the denominator, and this is rationalized. Okay, so the trick that I was telling you is this piece and this piece are always that number squared. So 3 squared, notice that is 9. And then this piece, root 5 squared, notice this is minus root 5 squared is 5. So you can use that trick if you recognize that these root parts are always going to cancel, which is nice. Okay, so that's a little trick. Our last example, we're going to rationalize the numerator by still multiplying by the conjugate. So if we do that in this problem, let's rewrite it so we have some room to work. The conjugate is now going to be the opposite, which is root r minus root 2. So I'm going to multiply top and bottom by root r minus root 2. And we'll throw some parentheses around there also. And again, we're going to FOIL. So when you FOIL in this type of problem, the O and the I always cancel. So we're actually just going to FOIL. We're just going to do the firsts and the lasts and then subtract them. So root r times root r is just r. That's my firsts. Root 2 times negative root 2 is negative root 4, which is just minus 2. And in the bottom, you can just distribute that 5. So you got 5 root r minus 5 root 2. So we rationalize the numerator. We typically usually just rationalize the denominator, but you might be asked to rationalize the numerator from time to time.